The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
All right, guys, let's get started with the next installment of our exciting journey into computer security. Today, we're actually going to talk about web security. Web security is actually one of my favorite topics to talk about because it really exposes you to the true horrors of the world. It's very easy to think as a student that everything will be great when you graduate. Today's lecture and the next lecture will be telling you that's in fact not the case. Everything is terrible. So, what is the web? Well, back in the olden days, the web was actually much simpler than it is today, right? So clients, which is to say the browsers, couldn't really do anything with respect to displaying rich interactive content. Basically, they could just get static images, static text, and that was about it. Now, the server side was a little bit more interesting, right? Because even if there was static content on the client side, maybe the server was talking to databases, maybe it was talking to other machines on the server side, things like that. And so for a very long time, the notion of web security basically meant looking at what the server was doing, right? And up to this point in this class, we've essentially taken that approach. So we looked at things like buffer overflow attacks, right? So how clients can trick the server into doing things the server doesn't want to do. We've also looked at the OKWS server, looked at how we can do some privilege isolation there. So we've sort of, up to this point, sort of looked at security through the history that was actually through the experiences that were actually experienced by the security researchers themselves. But now, actually, the browser is very interesting to think about in terms of security because the browser is super, super complicated these days, right? So now there's all kinds of insane dynamic stuff that the browser can actually do. So for example, you've probably heard of JavaScript, right? So JavaScript now allows pages to execute client-side code, right? It's Turing complete, can do all kinds of wacky stuff. There's the DOM model, which we'll talk about in more depth later today. The DOM model essentially allows JavaScript code to dynamically change the visual appearance of the page, fiddle with things like font stylings and stuff like that. There's XML HTTP requests. These are basically a way for JavaScript to asynchronously fetch content from servers. You may also hear XML HTTP requests referred to as AJAX, or asynchronous JavaScript fetching. There are things like WebSockets. This is actually a recently introduced API. So WebSockets essentially allow full duplex communication between clients and servers, right? Communication going both ways. We've got all kinds of multimedia support. So for example, we have things like the video tag, which allows a web page to play video without using a Flash applet. It can actually just play that video natively. There's also a geolocation. So now a web page can actually determine physically where you are. For example, if you're running a web page on a smartphone, the browser can actually access your GPS unit. If you're accessing a page on a desktop browser, it can actually look at your Wi-Fi connection and connect to Google's Wi-Fi geolocation service to figure out where exactly you are. That's kind of insane, right? But now web pages can do that kind of stuff. And so we've also talked about things like NACL, for example, which allows browsers to run native code. So there's many, many other features that I haven't mentioned here. But suffice it to say that the browser is now incredibly complicated. And so what does this mean from the perspective of security? Well, basically, it means that we're screwed, right? The threat surface for that right there is enormous. And loosely speaking, when you're thinking about security, you can think of a graph that sort of looks like this. So you've got the likelihood of correctness. And then you've got the number of features that you have. And so if this graph starts up here at 100, well, of course, we never even started at 100 even with very simple code because we can't even do bubble sort right. And so essentially that curve looks something like this, and web browsers are right over here. Right? And so as we'll discuss today, there's all kinds of wacky security bugs that are arising constantly, and as soon as the old ones are fixed, new ones are arising because people keep adding these new features, right? Oftentimes without thinking about what the security implications of those features are. And so if you think about what a web application is these days, well, it's this client thing and it's this server thing. And a web application now spans multiple programming languages, multiple machines, multiple hardware programs, right? You could be using Firefox on Windows, then it's going to go talk to a machine in the cloud that's running Linux, it's running the Apache server, maybe it's running an ARM chip as opposed to x86 or something like that, maybe the other way around. So long story short, there's all of these problems of composition. Right? There's all of these software layers and all of these hardware layers that all can impact security in some way, but it's also complicated. It's not quite clear how we can make sense of the entire whole. So for example, one common problem with the web is this problem of parsing context. So as an example, suppose that you had something in a page that looked like this. You declare a script tag. Inside that script tag, you declare a variable. There's some string here. And let's say that this string comes from an untrusted party, either the user or another machine or something like that. And then you close that script tag. Right? So this stuff is trusted, this stuff is trusted, this stuff is not trusted. So can anybody figure out why there might be some problems here if we take this untrusted string and put it in there?
You can have a closing quote mark in the untrusted strings, and then you have some malicious.
Right, exactly. So the problem is that there are multiple contexts that this entrusted code could sort of break into. So for example, if the entrusted code had a double quote here, now we've closed the definition of this JavaScript string, right? And so now we're out of the JavaScript string context and we're into the regular JavaScript execution context. So then the attacker can just put regular JavaScript code here and go to town, right? Alternatively, the attacker could just put a closing script tag here, right? And then at that point, the attacker can sort of get out of the JavaScript context, right, and then get into the HTML context, maybe define some new HTML nodes or something like that, right? And so you see this problem of composition all over the place in the web because there's so many different languages and runtimes we have to think about. HTML, CSS, JavaScript, maybe MySQL on the server side, so on and so forth. So this is just a classic example of why you have to do something called content standardization. So whenever you get untrusted input from someone, you actually need to analyze it very carefully to make sure that it's not being used as a vector for an attack. So another reason why web security is so tricky is because the web specifications are incredibly long, they're incredibly tedious, they're incredibly boring, and they're often inconsistent. And so by I mean the web specifications, I mean things like the definition of JPEG, the definition of CSS, the definition of HTML. These documents are like the size of the EU Constitution, right, and equally as easy to understand, right? And so what ends up happening is that the browser vendors, they see all these specs, and they essentially say, okay, thanks for that. I'm going to do something that somewhat resembles what these specs look like. Then they call it a day and they laugh about it with their friends. Okay, so what ends up happening is that these specifications end up being sort of like these vague aspirational documents that don't always accurately reflect what real browsers are doing. And if you want to understand the horror of this, you can go to this site called quarksmode.org. I mean, don't go to this site if you want to be happy, but you can go there and it actually documents all of these terrible inconsistencies that browsers have with respect to what happens when the user hits a key press, right? There should just be one key press event that's generated. You are so wrong. So go to quarksmode.org, you can check that out and see what's going on. So anyways, so in this lecture, we're going to focus on the client side of the web application. In particular, we're going to look at how we can isolate content from different web providers that has to coexist somehow on the same machine and the same browser. And so at a high level, there's this fundamental difference between the way you traditionally think of a desktop application and the way you think of a web application, right? Abstractly speaking, most of the desktop applications that you use, you can think of as coming from a single principle, right? So Word comes from Microsoft, and maybe TurboTax comes from Mr. and Mrs. TurboTax, so on and so forth. But when you look at a web application, something that looks to you visually as a single application is actually composed of a bunch of different content from a bunch of different people, right? So you go to CNN, it looks like it's all in one tab, but each piece of those visual things that you see may in fact come from someone different. So let's just look at a very simple example here. So let's say that we were looking at the following site. So HTTP foo.com, and we're just looking at index.html. So, you look at your browser tab, what might you see? So one thing that you might see is an advertisement. So you might see an advertisement in the form of a GIF, and maybe that was downloaded from ads.com. Then you also might see, let's say, an analytics library. And maybe this comes from google.com. And so these libraries are very popular for doing things like tracking how many people have loaded your page, looking to see where people click on things, to see like which parts of your site are the most interesting for people to interact with, so on and so forth. And you might also have another JavaScript library. Let's say it's jQuery. And maybe that comes from cdn.foo.com. So some content distribution network that foo.com runs. jQuery is a very popular library for doing things like GUI manipulation, things like that. So a lot of popular websites have jQuery, although they serve it from different places. And then in this page, you might see some HTML. And here's where you might see stuff like buttons for the user to click on, text input, so on and so forth. Right, so that's just raw HTML on the page. And then you might see what they call inline JavaScript from foo.com. And by inline, I just mean you have a script tag, and then you have a closed script tag, and then you just have some JavaScript code included in there directly, right? That's as opposed to where you say something like, script, and then the source equals something that lives on some server remotely, right? So this is what's called inline JavaScript. This is what's referred to as an externally defined JavaScript file. So you might have some inline JavaScript there from foo.com. And the other thing that you might have in here is actually a frame. So we'll talk about frames a bit more in a little bit. Think of a frame as almost like a separate JavaScript universe. Okay, it's a little bit equivalent to like a process in Unix. So maybe this frame here, maybe this guy belongs to HTTPS, Facebook.com, like this .html. And so maybe in here we have some inline JavaScript from Facebook. And then maybe we also have some image, so f.jpg that comes from HTTPS Facebook.com. Okay, so this is what a single tab might have in its contents. But as I just mentioned, all of this can potentially come from all these different principles. So there's a bunch of interesting questions that we can ask about an application that looks like this. So for example, can this analytics code from google.com actually access JavaScript state that resides in the jQuery code? Right? So to a first approximation, maybe that seems like a bad idea because these two pieces of code came from different places. But then again, maybe it's actually OK because presumably foo.com brought both of these libraries in so that they could work with each other. Right? So who knows? Another question you might have is, can the analytics code here actually interact with the text inputs here? So for example, can the analytics code define event handlers? Right? So a little bit of background on JavaScript. JavaScript is a single-threaded, event-driven model. So basically, there's just, in each frame, there's just an event loop that's just constantly pulling events, key presses, network events, timers, and stuff like that, and then seeing if there are any handlers associated with those events, and if so, it fires them, right? So who should be able to define event handlers for this HTML? Should Google.com be able to do it? It's not from foo.com, so maybe not. Right? Another question too is, what's the relationship between this Facebook frame here and the larger frame? Right? The Facebook frame is an HTTPS, right? Secure. Foo.com is an HTTP, right? Non-secure. So how should these two things be able to interact? So basically, to answer these questions, browsers use a security model called the same origin policy. And so there's sort of this vague goal, right? Because a lot of things with respect to web security are kind of vague because nobody knows what they're doing. But the basic idea is two websites should not be able to tamper with each other unless they want to. And so defining what tampering means was actually easier when the web was simpler, right? But as we keep adding these new APIs, it's more and more difficult to understand what this non-tampering goal means. So for example, it's obviously bad if two websites which don't trust each other can sort of overwrite on each other's visual display, right? That seems like an obviously bad thing. It seems like an obviously good thing if two websites which want to collaborate are able to somehow exchange data in a safe way, right? So you can think of mashup sites you may have heard of. So sometimes you'll see these things on the internet. It's like someone takes Google Map data and then takes, the location of food trucks. And then you have this amazing mashup that allows you to eat cheaply and avoid salmonella, right? So that seems like a thing you should be able to do. But how exactly do we enable that type of composition? Then there's other things that are kind of hard to say. So for example, if JavaScript code comes from origin X and it's inside of a page that's from origin Y, how exactly should that code and that content compose? So the strategy that the same origin policy uses, it can be roughly described as follows. So each resource is assigned an origin, which we'll discuss in a second. And essentially, JavaScript code can only access resources from its own origin. And so this is the high-level strategy the same origin policy uses, but the devil's in the details, and there's just a ton of exceptions, which we're going to look into in a second. But first of all, before we proceed, let's define what an origin is. So an origin is basically network protocol scheme plus host name plus port. So for example, we could have something like HTTP, foo.com, and then maybe it's index.html. Right? So the scheme here is HTTP. The host name is foo.com, and the port is 80. Now the port in this case is implicit. Right? The port is the port on the server side that the client uses to connect. Right? So if you see a URL from the HTTP scheme and there's no port that's explicitly supplied, then implicitly that port is 80. Okay? So then if we look at something like HTTPS, once again, foo.com, index.html. So these two URLs have the same host name, right? But they have actually different schemes, right? HTTPS versus HTTP. And also here, the port is implicitly 443, right? That's the default HTTPS port, right? So these two URLs have different origins. And then As a final example, if you had a site like http bar.com, then you can use this colon notation here, 8181. Whatever, these things beyond here don't matter with respect to the same origin policy, at least with respect to this very simple example. Here we see that we have a scheme of HTTP, a host name of bar.com, and here we've explicitly specified the port. So in this case, it's a non-default port of 8181. So does that make sense? It's pretty straightforward. OK, so this is basically what an origin is. Loosely speaking, you can think of an origin as a UID in Unix, with the frame being loosely considered as like a process. So there are 4 basic ideas behind the browser's implementation of the same origin policy. So first idea is each origin has client-side resources. And so what are examples of those resources? Things like cookies. Now you can think of cookies as a very simple way to implement state in a stateless protocol like HTTP. Basically, a cookie is like a tiny file that's associated with each origin. We'll talk about the specifics of this in a bit. But the basic idea is that when the browser sends a request to a particular website, it includes any cookies that the client has for that website, right? And you can use things. You can use these cookies for things like implementing, password remembering. Maybe if you're going to an e-commerce site, you can remember stuff about a user's, shopping cart and these cookies, so on and so forth. So cookies are one thing that each origin can be associated with. Also, you can think of DOM storage as another one of these resources. This is a fairly new interface, but think of DOM storage as just a key value store. Right? So DOM storage allows an origin to say, for this given key, which is a string, let me associate it with this given value, which is also a string. Another thing that is associated with an origin is a JavaScript namespace. Right? So that JavaScript namespace defines what functions and what interfaces are available to that origin. Right? Some of those interfaces are built in, like let's say the string prototype and stuff like that. And then an application might actually fill the JavaScript namespace with some other content. There's also this thing called the DOM tree. So DOM is short for Document Object Model. And the DOM tree is essentially a JavaScript reflection of the HTML in a page. Right? So you can imagine that the DOM tree has a node for the topmost HTML node in the HTML, and then it's going to have a node for the head tag. Then it's going to have a node for the body tag, right? So on and so forth. So the way that a lot of dynamic web pages are made dynamic is the JavaScript code can access this data structure in JavaScript that mirrors the HTML content. So you can imagine an animation takes place by changing some of these nodes down here to implement different organizations of various tags, right? So that's what the DOM tree is. There's also a visual display area. Although we'll see that the visual display area actually interacts very strangely with the same origin policy, so on and so forth. So at high level, each origin has access to some set of client-side resources of these types. Right? Does that make sense? And then the second big idea is that each frame gets the origin of its URL. Right? So as I mentioned before, a frame is roughly analogous to a process in Unix. It's kind of like a namespace that aggregates a bunch of other different resources. So the third idea is that scripts so JavaScript code, execute with the authority of its frame's origin. Okay, so what that means is that, foo.com imports a JavaScript file from bar.com. Well, that JavaScript file is going to be able to act with the authority of foo.com. And so, loosely speaking, this is sort of similar to, if you were in the Unix world to run a binary that sort of belonged in someone else's home directory, right? That thing would sort of execute with your privileges there. And the fourth thing is there's passive content. So by passive content, I mean things like images, for example, right? Or CSS files or things like that. These are things which we don't think of as having executable code. So passive content gets zero authority from the browser. So that kind of makes sense. We'll see why this fourth thing is a little bit subtle in a second. So going back to our example here, so we see, for example, that the Google Analytics script, right, and the jQuery script, they can access all kinds of stuff in foo.com. So for example, they can read and write cookies. They can do things like attach event handlers to buttons here, so on and so forth. If we look at the Facebook frame and its relationship to the larger foo.com frame, then we see that they're from different origins, right? Because they have different schemes here. They have different host names, right? Different ports. So what this means is that they are, to a first approximation, isolated, right? Now, they can communicate if they both opt into it using this interface called post message. So post message allows two different frames to exchange asynchronous immutable messages with each other. So think of this facility as allowing Facebook to try to send a string, not a reference, a string up to the enclosing foo.com frame. Now note that if foo.com doesn't want to receive those messages, it doesn't have to, right? So this has to be opt-in from both sides to get this thing to work. So note that the JavaScript code here in the Facebook frame, it cannot issue an XML HTTP request to the foo.com server, right? That's once again because network destinations also have these origins that are associated with them. And so because Facebook.com does not have the same origin as foo.com, it can't asynchronously fetch stuff from it via XML HTTP requests. And so the last thing we can look at, we can see, OK, we've got an image up here from ads.com. This is rule number 4 over there, so it seems pretty straightforward. This is an image. It has no executable code, so clearly the browser should give it no authority. Now, that seems kind of like a dumb thing. Like, why are you even talking about images having authority or not having authority? It seems obvious that images shouldn't be able to do stuff. Well, this is a security class, right? So clearly, there is mischief that hides in statement number 4 up there. So what happens if the browser incorrectly parses an object and misattributes its type, right? So you can actually get into security problems there. And this was actually a real security problem. So there's this thing called the MIME sniffing attack. So the MIME type, I mean, you've probably seen these before. It's something like, text.html or, image.jpg, things like that. So it's like a MIME type. And so old versions of IE used to do something that they thought was going to be helpful for you, right? So sometimes what web servers will do is they will misattribute the file extension of an object, right? So you can imagine that a web server that's been configured incorrectly, it might attach a .html suffix to something that's really an image, right? Or it might attach a .jpg suffix to something that's really HTML. So what IE would do back in the olden days is try to help you out, right? So IE will go out, it would go fetch this resource, and it would say, OK, this resource claims to be of some type according to its file name extension, right? But then it would actually look at the first 256 bytes of what was in that object. And if it found certain magic values in there that indicated that there was a different type for that object, it would just say, hey, I found something cool here. The web server misidentified the object. Let me just treat the object like its type that I found in these first 256 bytes, and then everybody's a winner, right? Because I've helped the web server developer out, because now their website's it's gonna render properly, and the user's gonna like this because they get to unlock this content that would have been garbage before, right? But this is clearly a vulnerability, right? Because suppose that a page includes some passive content, right? Like, let's say an image from a domain that's controlled by the attacker. Now, from the perspective of the victim page, it's saying, even if this attacker site is evil, it's passive content. It can't do anything, right? Like, at worst, it displays like an unfortunate image, but it can't actually access any code because passive content gets zero authority, right? But what would happen is that IE could sniff this image, the first 256 bytes, and the attacker could intentionally put HTML and JavaScript in there, right? So what would happen is that the victim site brings in what it thinks is an image, IE coerces it into HTML and JavaScript, and then executes that code, right, in the context of that enclosing page, right? So does that attack make sense? Right? And so this is sort of an example of how complex browsers are, and how adding even a very sort of well-intentioned feature can cause these very sort of subtle security bugs, right? So let's now sort of dig down and take a deeper look at how the browser secures various resources. So let's look at frames and window objects. So frames represent these sort of separate JavaScript universes that we discussed over here. I mean, implementation-wise, a frame with respect to JavaScript is an instance of a DOM node, right? So I forget where I drew. Oh yeah, this DOM node up here. So the frame would exist as a DOM node object somewhere in this hierarchy that's visible to JavaScript. In JavaScript, the window object is actually an alias for the global namespace. It's kind of this wacky idea. But like, if you define this global variable named x, you can also access it via the name window.x. Okay? So basically, frames and window objects are very powerful references for you to be able to access. And they actually contain pointers to each other, right? The frame contains a pointer to the associated window object and vice versa. So these two things are essentially equivalently powerful. So frame and window objects, they get the origin of the frame's URL. Or, right, because there's always an or in web security, they can get a suffix of the original domain name, the original origin. So, for example, a frame could start off having an initial origin x.y.z.com, right? And so let's ignore the scheme and the protocol for a second. So initially, the page could start off like this. It can then intentionally say, I want to set my origin to be y.z.com, a suffix of that, right? And the way that it indicates this is by doing an assignment to the special document .domain value that's accessible via JavaScript. So it can set document.domain explicitly to this right here, right? And that's allowable because this guy is a suffix of that guy. And then similarly, it could also set document.domain to z.com and effectively reset its origin like that. Now, what it cannot do is it cannot do something like setting document.domain to a.y.z.com. That's disallowed because this is not a proper suffix of the original origin. And also, it cannot set its suffix to .com. So does anyone have any theories about why this is a bad idea? Right, exactly. So people are laughing because clearly this is going to bring out the apocalypse, right? So if it does this, and this means that the site could somehow be able to impact cookies or things like that in any .com site, which would be pretty devastating. The motivation for why these types of things are allowable is because presumably these origins have some type of pre-existing trust relationship. So this seems to be vaguely okay, whereas this would seem to be bad.
So you can make these splits on any dot, or actually at any point. Like
No.
for example, for x.y.zz.com, can you change that to z.com?
No, so it's on every dot.
Okay.
Is there a reason that it wasn't made so that you could specify any super subdomain, but the but somehow they had to agree on where the information was coming from? So like you said some kind of, I want to consider all of these to be same origin as me, and so any of them can impact me. And then you need it symmetric in order for me to impact them as well. So setting .com means anything that's .com can impact me, and then you both need to set .com to agree.
Yeah, it's tricky. So there's a couple different answers to that. So first of all, people were very worried about this attack here, and so they wanted to sort of make the domain manipulation language be at least somewhat easy to understand. So they don't sort of allow more Baroque settings. I'll get to one thing in a second which kind of allows what you're talking about, but only with respect to domain suffixes. So I'll get to that one second. And another thing to mention too is that the post message interface does allow arbitrary domains to communicate with each other if they both opt into it. So in practice, people use post message to do cross-domain communication if they can't sort of set their origins to be the same using these tricks here. So okay, so browsers can constrain or more like widen, I should say, their domain to these suffixes of the original domain. And there's also this little interesting quirk here, which is that browsers actually distinguish between a document .domain value that has been written and one that has not been written. Okay, and there's a subtle reason for this, which I'll get into in a second. So basically, two frames can access each other if one of two things is true, right? The first thing is both of the frames set document.domain to the same value. And the other way that two frames can access each other is if neither of those frames has changed document domain. And of course, both values have to match. So, and there's a value match. So the reason for this is a bit subtle, but the basic idea is that these two rules prevent a domain from being attacked by one of its own buggy or malicious subdomains. Okay, so imagine that you have the domain x.y.z.com, and then imagine that it's trying to attack y.z.com, right? So this guy up here is buggy or evil. So what this guy could try to do is actually shorten his domain to be y.z.com and then start messing around with JavaScript state or cookies or stuff like that here, right? And so basically what these two rules over here will say is that if y.z.com does not want to actually allow anyone to interact with it, it will never change its document.domain value, right? So that when this frame up here does shorten it, the browser will say, aha, you've shortened it. You have not. There's a match here in terms of the values, but this person hasn't indicated they want to opt in into this type of chicanery. So does that make sense? OK, so that is basically how frames work with respect to the same origin policy. So then we can look at how are DOM nodes treated. So DOM nodes, it's pretty straightforward for DOM nodes. So DOM nodes basically get the origin of their surrounding frame. Makes sense. Then we can look at cookies. Cookies are complicated and a bit tricky. So cookies, they have a domain, and they have a path. So for example, you can imagine a cookie might have be associated with the following information. So asterisk.mit.edu and then 6.858, right? So you've got sort of this domain thing sitting here, and then you've got this path thing sitting over here. And so note that this domain can be possibly complete suffix of the page's current domain. So you can play somewhat similar tricks as we had over there. And note that this path here can actually just be set to just to the slash with nothing else there, which indicates that all paths in the domain should be able to have access to this cookie here. But in this case, we actually have one of these non-empty paths. And so whoever sets this cookie, right, basically gets to choose what the domain and the path look like. And it can actually be set by the server or can be set on the client side. So on the client side, you can basically write to this JavaScript object called document.cookie. And there's sort of this Byzantine format that you can use to indicate all these paths and things like that. But suffice it to say, it can be done. So JavaScript can set cookies like this. And also the server can actually set cookies on HTTP responses when they come back over the wire. So you can basically just use the set cookie header if you're the server to set some of these things. And note that there's also a secure flag that you can set in the cookie to indicate that it's an HTTPS cookie, right? Meaning that HTTP content should not be able to access that cookie. And so that's the basic idea behind cookies. Now note that whenever the browser generates a request to a particular web server, it's going to include all of the matching cookies in that request. So there's a little bit of sort of like string matching algorithms that have to take place to figure out, what are all the exact cookies that should be sent to the server for a particular request, because you can have all of these weird sort of suffix domain things going on and so on and so forth. But that's the basic idea behind cookies. So does that all make sense?
Right, so can frames access each other's cookies if they match those rules?
Yeah, so frames can do that, but it's dependent on how the document.domain has been set, and then it's dependent on what the cookies, domain, and path have been set. So yeah, so after a bunch of these sort of string sort of comparisons, yes, frames can access each other's cookies if all those tests pass. Okay, so yes, that leads me into the next question. So we're trying to figure out how different frames can access each other's cookies. So what's the problem? What would be the problem if we allowed arbitrary frames to write arbitrary people's cookies? So what do you think? Well, it would be bad, suffice it to say, right? The reason it would be bad is because, once again, these cookies allow the client side of the application to store per user data, right? So you can imagine that if an attacker could control or overwrite a user's cookie, the attacker could actually, for example, change that cookie for Gmail to make the user log into the attacker's Gmail account, right? And so when the user logged into the attacker's Gmail account, any email that the user typed in could be read by the attacker, for example. You could also imagine that someone could tamper with your Amazon.com cookie, put all kinds of embarrassing or ridiculous stuff in your shopping cart, perhaps, or so on and so forth. So cookies are actually a very important resource to protect, and a lot of web security attacks try to steal that cookie, right, to do various kinds of evil. So here's another interesting question with respect to cookies. So let's say that you've got the site that's coming from foo.co.uk. So should a site from this host name be allowed to set a cookie for co.uk? Right? So this is a bit subtle because, according to the rules that we've discussed before, a site from here should be able to, shorten its domain, right? Set a cookie for this, and that all seems to be legal. Now, of course, as a human, we think this is kind of suspicious, right? Because as a human, we actually understand that this is, morally speaking, a single atomic domain, right? Morally speaking, this is equivalent to .com, right? The British got screwed, they have to have a dot in there, but that's not their fault. History's unfair, right? So morally speaking, this is a single domain, right? So you actually have to have some special infrastructure to get the cookie setting rules to work out correctly, right? So essentially Mozilla, they have this website called publicsuffix.org. And basically, what this website contains are lists of these rules for, how cookies and origins and domains should be shrunk, given that, some things might have dots in them, but actually they should be treated as a single sort of atomic thing, right? And so actually, when your browser is figuring out, how it should do all these various cookie manipulations, it's actually going to consult this site, or it's going to have this baked in somehow or something like that to make sure that foo.co.uk can't actually just shorten its domain to co.uk and then perform some chicanery. So once again, this is very subtle. And a lot of the interesting web security issues that we find come about because a lot of the original infrastructure was designed just for the English language, for ASCII text or something like this. It wasn't designed for an international community, right? And so as the internet became more popular and people said, hey, we made some pretty big design decisions here at the beginning, we should actually make this usable by people who don't use our narrow understanding of what language means, you run into all of these crazy problems. And I'll give you another example of one of those later in the lecture. So does this all make sense? Okay. So with respect to XML HTTP responses, so how are they treated by the same origin policy? So by default, JavaScript can only generate one of these if it's going to its origin server. Okay. However, there's this new interface called cross-origin request, or CORS. Right. So this is same origin unless the server has enabled this CORS thing. And so basically, this adds a new HTTP response header called access control allow origin. Right? So let's say that JavaScript from foo.com wants to make an XML HTTP request to bar.com. Right? So that's cross-origin, as we've described in the rule so far. So if the server in bar.com wants to allow this, it will return in its HTTP response this header here that's going to say, yes, I allow, for example, foo.com to send me these cross-origin XML HTTP requests, right? The server in bar.com could actually say no. It could refuse the request, right? In which case the browser would sort of fail the XML HTTP request. So this is sort of a new thing that's come up, in large part because of these mashup applications, this need for somehow applications from different developers in different domains to be able to share data in some type of constrained way. Right? So this could also be asterisks over here if anybody can fetch the data across origin, so on and so forth. So I think that's pretty straightforward. So I mean, there's a bunch of other resources we could look at. For example, images. So a frame can load images from any origin that it desires, but it can't actually inspect the bits in that image. Right? Because somehow the same origin policy says that having different origins directly inspect each other's content, that's a bad thing. So the frame can't inspect the bits, but it can actually infer things like what the size of the image is, right? Because it can actually see where the other DOM nodes in that page have been placed, for example. So this is another one of these weird instances where the same origin policy is ostensibly trying to prevent all information leakage, but it can't actually prevent all of it because embedding inherently reveals some types of information. CSS has a similar story to images. So a frame can embed CSS from any origin. However, it cannot directly inspect the text inside that CSS file if it's from a different origin. But it can actually imply what the CSS does because it just can create a bunch of nodes and then see how their styling gets changed. right? So it's a bit wacky. JavaScript is actually my favorite sort of example of how the same origin policy kind of struggles to maintain any type of intellectual consistency. So the idea here is that if you do a cross-origin fetch of JavaScript, that is allowed. You can allow that external JavaScript to execute in the context of your own page. You cannot, however, look at the source code for it, right? So if you have, a script tag, source equals something outside your domain, then when that source gets executed, you can call functions in it, but you can't actually look at the JavaScript source code in it. Okay, fine. So that seems very nice. However, there are a bunch of holes to this. So for example, JavaScript is a dynamic scripting language, and functions are first-class objects. So for any function, f, you can just call f.toString, and that will give you the source code for the function. And people do this all the time to do things like implement dynamic rewriting and stuff like that. So even though the same origin policy doesn't allow you to directly look at the contents of the script tag itself, you can just call this for any public function that external script has given you and just get the source code like that, right? Another thing you could imagine doing is you could just get your home server from your domain to just fetch the source code for you and then just send it back to you, right? So oops, you essentially just ask your home server to run wget, and you get the source code that way. Okay, so that's kind of goofy. So long story short, the same origin policies here are a bit odd. Yeah?
Presumably part of the reason they do it is to prevent the user from fetching JavaScript, because then cookies will be sent as well, so you can get JavaScript that's tailored to you.
Yeah.
So if you get your server to fetch it for you, it won't have the user's cookie, so that's probably safe.
That is true, although in practice, a lot of times the raw source code itself is not user tailored. Right. In practice, but you're right that it will prevent sort of cookie-mediated attacks like that, modulo some of the cookie stealing attacks we'll talk about later. But that's exactly correct. So anyway, so because it's actually pretty easy for users and applications to get JavaScript source code, a lot of times JavaScript source code, when it's deployed, it's actually obfuscated and minified. So if you've ever sort of tried to look and see how a web page works, if you look at the source, sometimes people will do things like remove all the white space. Right? They will also change all the variable names to be super short and have all these exclamation marks. Looks like cartoon characters cursing in the cartoons, right? And so that's sort of a cheap form of digital rights management. But I mean, it's all ultimately a bit of a crapshoot, because you can do things like execute that code in your own browser, see what it does, sniff the network, see who it talks to, so on and so forth. But that's basically the same origin story for JavaScript. Plugins. Yeah.
I was under the impression that the reason you do that is the short variable name is just going to take less time to download rather than
So that is also a reason they do that too. That's a good point. But there are if you type into the internet sort of web page obfuscation or stuff like that, people often try to somehow bake some type of secrets into either their HTML or their JavaScript. Maybe they want to obscure the protocol, for example, that the client uses to talk to the server. So people will also do the obfuscation for that reason. Pure minification, in other words, just making the variable name small and removing the white space. Yeah, that's mainly just to save download bandwidth, download time. Okay, so that's a story for JavaScript. There's also plugins. So this is stuff like Java and things like this. So Frame can basically run a plugin from any origin. Now plugins, depending on who you believe, are actually going the way of the dinosaurs, right? Because a lot of the new HTML5 features, like the video tag and things like this, can actually do stuff that you used to only be able to do with a plugin like Java. So it's not clear how much longer these things are going to be around. Okay, so any questions? Okay, so remember that when the browser generates an HTTP request, it automatically includes the relevant cookies in that request. So what happens if a malicious site generates a URL that looks like this? So for example, it creates a new frame, a new child frame. It sets that URL to bank.com. And then it actually tries to mimic what the browser would do if there was going to be a transfer of money between the user and someone else. Right? So in this URL, in this frame that the attacker's trying to create, it tries to invoke this transfer command here. It's saying $500, and that should go to the attacker's account at the bank, right? Now, the attacker page, which the user visited because somehow the attacker has lured the visitor to go there. What's interesting about this is that even though the attacker page won't be able to see the contents of this child frame, right, because it's probably going to be in a different origin, the bank.com page will still do what the attacker wants, right? Because the browser is going to transfer all the user's cookies with this request. It's going to look at this command here and say, oh, the user must have somehow asked me to transfer $500 to this mysteriously named individual named attacker. OK, I'll do it, right? Seems reasonable. So that's a problem. The reason this attack works is because essentially the attacker can figure out deterministically what this command should look like, right? There's no randomness in this command here. So essentially what the attacker can do is try this on his or her own bank account, figure out this protocol, and then just somehow force the user's browser to execute this on the attacker's behalf. So this is what's called a cross-site request forgery. And so sometimes you hear this called CSRF, CSRF. And so the solution to fixing this attack here is that you actually just need to include some randomness in this URL that's generated, a type of randomness that the attacker can't guess statically. So for example, you can imagine that inside the bank's web page, it's going to have some form, right? The form is the thing which actually generates a request like this. So maybe the action of that form is transfer.cgi. And then inside this form, you're going to have an input. Inputs are usually used to get in user input like text, key presses, mouse clicks, stuff like that. But we can actually give this input a type of hidden, which means that it's not shown to the user. And then we can give it this attribute. We'll call it CSRF. And then we'll give it some random value. A72F, whatever, right? And so remember, this is generated on the server side, right? So when the user goes to this page, on the server side, it somehow generates this random token here, right? And embeds that in the HTML that the user receives. So when the user submits this form, then this URL that we have up here will actually have this this extra thing up here, which is the this token here, right? And so what this does is that this now means that the attacker would have to be able to guess the particular random token that the server had generated for the user each time the user had gone to the page, right? And so if you have sufficient randomness here, the attacker can't just forge one of these things. Because if the attacker guesses the wrong token, then the server will just reject the request.
Why should these values be encoded in the URL and not in the body of the HTTP request? And if using HTTPS.
Yeah. So HTTPS helps with a lot of these things, right? And there's actually no intrinsic reason why you couldn't put some of this stuff in like the body of the request. There's like some legacy reasons why forms sort of work like this. But you're correct that in practice, you could put that information somewhere else in the HTTP request. But note that just moving that information, for example, to the body of the request, there's still a challenge there potentially, right? Because if there's something there that the attacker can guess, then the attacker may still be able to somehow conjure up that URL. For example, by making an XML HTTP request and then explicitly setting the body to this thing that the attacker knows how to guess.
If the attacker just gives you a URL, that just gets encoded in the header of the request, not the body.
If the attacker just gives you a URL. So if you're just setting a frame to a URL, right, then basically that's all that the attacker can control, right? But if you're using an XML HTTP request, if somehow the attacker can generate one of those, then XML HTTP interface actually allows you to set the body.
But XML HTTP request would be limited by same origin. But the attacker could just write a form and submit it. There's nothing stopping them from automatically submitting a form, like using post, and then it's sent in the body, but it's still.
That's right. So XML HTTP request is limited to the same origin. However, if, for example, the attacker can maybe do something like this, for example, right, then the attacker could inject the XML HTTP request here, which would then execute with the authority of the embedded page.
Can the attacker get the random value by inspecting the HTML source code?
Yes, that's actually a good question, right? So it depends on what the attacker has access to. If the attacker, for example, by doing something goofy like that, can actually access this JavaScript property called inner HTML, this is a property of all DOM nodes, right? So if I call like document.body.inner HTML, I will get all of the HTML that's inside of that page right now. So yeah, so if the attacker can do this, then yeah, then you're in trouble. That's right. So a lot of these details, though, depend on exactly what the attacker can and can't do, right? Which kind of makes sense, right? So if the attacker can or cannot generate AJAX requests, that means one thing. If the attacker can or cannot look at the raw HTML, that means another thing, so on and so forth. All right. So this token-based thing is sort of a popular way to get around these CSRF attacks. All right, so another thing we can look at are network addresses. And so this gets into some of the conversations we've been having about who the attacker can and not contact via XML HTTP request, for example. So with respect to network addresses, a frame can send HTTP and HTTPS requests to a host plus a port that matches its origin. But note that the security of the same origin policy is actually very tightly tied to the security of the DNS infrastructure, right? Because all the same origin policy's rules are based upon what names mean. Right? So if you can control what names mean, you can actually launch some pretty vicious attacks. So an example of this is the DNS rebinding attack. Right? So in this attack, the goal of the attacker is run attacker-controlled JavaScript with the authority of some victim website. Let's call them victim.com. Right? So the attacker wants to bust the same origin policies and somehow run code that he has written with the authority of some other site. So here's the approach. So the first thing that the attacker is going to do is register a domain name. So let's say we just call that attacker.com. Right? Very simple to do. Just pay a couple of bucks. You're ready to go. You own your own domain name. And so note that the attacker is also going to set up a DNS server to respond to name resolution requests for objects that reside in attacker.com. So the second thing that has to happen is that the user has to visit attacker.com. In particular, the user has to visit some website that hangs off of this domain name, right? This part is actually not tricky, right? So you can create an ad campaign, free iPad. Everybody wants a free iPad, even though nobody knows everyone who's ever wanted a free iPad. They click on this, they're there, right? Send a phishing email, so on and so forth. This part's not hard, right? So what's going to happen? So this is actually going to cause the browser to generate a DNS request to attacker.com. Right? Because this page has some objects that refer to some objects that live in attacker.com. The browser is going to say, I've never seen this domain before. Let me send the DNS resolution request to attacker.com. Right? So what's going to end up happening is that the attacker's DNS server is going to respond to that request, right? But it's going to respond with the DNS result that has a very short time to live. okay? Meaning that the browser will think that it's only valid for a very short period of time before it has to go out and revalidate that, okay? So in other words, the attacker response has a small TTL. Okay, fine. So the user gets the response back. The malicious website is now running on the user side. Meanwhile, while the user is interacting with the site, the attacker is going to configure the DNS server that he controls. The attacker is going to bind the attacker.com name to victim.com's IP address. Right? So what that means is that now, if the user's browser asks for a domain name resolution for something that resides in attacker.com, it's actually going to get some internal address to victim.com. Right? This is actually very subtle. Now, why can the attacker's DNS resolver do that? Because the attacker configures it to do so. Right? The attacker's DNS server does not have to consult victim.com to do this rebinding. Right? So perhaps you can see sort of the outline of the attack now. So what will happen is that the website wants to fetch a new object. Via, let's say, via AJAX, right? And it thinks that that AJAX request is going to go to attacker.com somewhere externally, but this AJAX request actually goes to victim.com. Right? And the reason why that's bad is because now we've got this code on the client side that resides on the attacker.com webpage, right? That's actually accessing now data that is from a different origin, from victim.com, right? And so once this step of the attack completes, then the attacker.com webpage can, send that content back to the server using CORS or do other things like that, right? So does this attack make sense?
Wouldn't it be more sensible to do the attack the other way around? So to map victim.com to the attacker's IP address? Because that way you're same origin as victim.com, so you can get all the cookies and such.
Yeah, so that would work too as well. So what's nice about this though is that presumably this allows you to do nice things like port scanning and stuff like that. I mean, your approach will work, right? But I think here the reason why you do because essentially you can do things like constantly rebind what attacker.com points to different machine names and different ports inside of victim.com's network, right? And so then you can sort of step through. So in other words, let's say that the attacker.com webpage always thinks it's going to, attacker, we'll just say it's just going to attacker.com and issuing an AJAX request there. So every time the DNS server rebinds, it can set this to some different IP address inside of victim.com's network. Right? So it can just sort of step through the IP addresses one by one and see if anybody's responding to those requests.
But the client, the user you're attacking doesn't necessarily have inside access to victim.com's network.
So what this attack typically assumes is that there are certain firewall rules that would prevent attacker.com from outside the network from actually looking through each one of the IP addresses inside of victim.com. However, if you're inside CorpNet, if you're inside the corporate firewall, let's say, then machines often do have the ability to sort of contact arbitrary machines. Yeah, exactly.
Does this work over HTTPS?
So that's an interesting question. So HTTPS, right, has these keys, right? And so the way you'd have to get this to work with HTTPS is if somehow, for example, if attacker.com could, let me think about this. Yeah, it's interesting because presumably if you're using HTTPS, then when you sent out this AJAX request, the victim machine wouldn't have the attacker's HTTPS keys, right? So the cryptography would fail somehow, right? So I think HTTPS would stop that.
Or if the victim only has things on HTTPS.
Yeah, so I think that'd stop it.
If you configure the detector to call a CNAME record, would the browser use the initial or the CNAME result when it develop the server?
That's a good question. I'm actually not sure about that. So it actually, a lot of these attacks sort of depend on the devil in the details, right? So I'm not actually sure how that would work.
It uses the first one.
It would use the first domain? Okay. Yep.
So why can't the attacker respond with the victim's IP address in the first place? Why?
So why can't, what do you mean?
Run their own code.
Why does the attacker DNS server has to respond with the attacker's IP in there?
Oh, well, yeah. So the attacker has to somehow get its own code on the victim machine first before it can then start doing this nonsense where it's looking inside the network. So there's that initial step where it has to put that code on the victim's machine. All right, so this is just the time. Let's keep moving forward, though, but come see me after class if you want to pull up the question. All right, so that's the DNS rebinding attack. So how can you fix this? So one way you could fix it is so that you modify your client-side DNS resolvers so that external host names can never resolve to internal IP addresses, right? It's kind of goofy that someone outside of your network should be able to create a DNS binding for something inside of your network. So that's kind of the most straightforward solution. You could also imagine that the browser could do something called DNS pinning, whereby if it receives a DNS resolution record, then it will always treat that record as valid for, let's say, 30 minutes, regardless of whether it has a short TTL set inside of it. So that also prevents the attack as well. That solution is a little bit tricky because there are some sites that actually intentionally use dynamic DNS to do things like load balancing and stuff like that. So the first solution is probably the better one. OK, so here is sort of a fun attack. So we've talked about a lot of resources that the origin protects, the same origin policy protects. So what about pixels? So how does the same origin policy protect pixels? Well, as it turns out, pixels don't really have an origin. So each frame gets its own little bounding box, right? Just a square, basically. And so a frame can draw wherever it wants on that square, right? So this is actually a problem, because what this means is that a parent frame can draw atop of its child frame. Right? So this can lead to some very insidious attacks. So let's say that the attacker creates some page. And let's say inside of that page, the attacker says, click to win the iPad, the very standard thing. So this is the parent frame. Now, what the parent frame can do is actually create a child frame, right, that is actually the Facebook like button frame. Right? So Facebook allows you to run this little piece of Facebook code you can put on your page. If the user clicks like, then that means that it'll go on Facebook and say, hey, the user's liked this particular page. So we've got this child frame over here. That actually turned out remarkably well. Anyway, so you've got this like thing over here. Now what the attacker can do is actually overlay this frame on top of the click to get the free iPad, and also make this invisible, right? So CSS lets you do that, right? So what's going to happen? As we've already established, everybody wants a free iPad. So the user's going to go to this site, click on this thing, this area of the screen, right? Thinking that they're going to click here and get the free iPad. But in reality, they're clicking the like button that they can't see. That's invisible. That's like layered atop the Z index, right? And so what that means is that now, maybe they go check their Facebook profile and they've liked attacker.com, and they don't remember how that happened, right? So this is actually called clickjacking attack. As you can imagine, you can do all kinds of evil things here. So you can imagine, like, if there was you could steal passwords this way, you could get raw input. I mean, it's madness, right? And so once again, this happens because the parent essentially gets the rights to draw over anything that's inside of its bounding box, right? So does that attack make sense? Yeah.
Sorry, what do you mean the parent gets to draw over anything?
So what I'm trying to indicate here is that visually speaking, like what the user just sees is this. Okay.
Oh, that's the parent.
Yeah, this is the parent frame, that's right, this is the child frame. So visually speaking, the user just sees this. But using the miracle of my Da Vinci style drawing techniques, this is actually overlaid atop this transparently, right? And so that's the child frame, that's the parent frame. Okay, so there's a couple different solutions you can imagine for solving this. The first solution is to use frame busting code. So you can actually use JavaScript expressions to figure out if you have been put into a frame by someone else. So like one of these tests is you compare the reference self to top. So in the JavaScript world, self refers to the frame that you yourself are in. Top refers to the frame at the top of the frame hierarchy, right? So if you do this test and you find out that self is not equal to top, then you realize that you are a child frame, and then you can refuse to load or do things like this. So this, in fact, is what will happen if you try to create a frame for, let's say, CNN.com. You can actually look in the JavaScript source and see that it does this test, right? Because CNN.com doesn't want other people taking credit for its content. So it only wants to be the topmost frame. So that's one solution you can use here. The other solution that you can use here is also to have your web server send this HTTP response header called xframe options. Right? So when the web server returns a response, it can set this header, and it can basically say, hey, browser, do not allow anyone to put my content inside of a frame. And so that allows for the browser to do the enforcement. So that's pretty straightforward. So there's a bunch of other sort of crazy attacks that you can launch. Here's another one that's actually pretty funny. So as I was mentioning before, the fact that we're now living in a web that's internationalized actually means that there's all these issues that come up involving naming and how you represent host names. So for example, let's say that you see this letter right here, right? So what does this look like? This looks like a C, right? But is this a C in ASCII in the Latin alphabet, or is this a C in Cyrillic? Hard to say, right? And so you can end up having these really strange attacks, right, where attackers will register, a domain name like cats.com, for example, but this is a Cyrillic C, right? And so users will go to this domain, right? They might click on it or whatever, thinking they're going to Latin alphabet C, right, cats.com, but instead they're going to an attacker one, right? And then all kinds of madness can happen from there as well, right? And so you might have heard of attacks like this, or like typo squatting attacks, where people register for names like FCEbook.com, right? This is a common like fumble finger typing for Facebook.com. And so, if you control this, you're going to get a ton of traffic from people who think they're going to Facebook.com, right? And so there's a bunch of different sort of wacky attacks that you can launch through the domain registry system that are sort of tricky to defend from first principles, because how are you going to prevent users from mistyping things, for example? Or how would the browser indicate to the user, like, hey, this is Cyrillic? Is the browser going to alert the user every time Cyrillic fonts are included? That's going to make people angry if they actually use Cyrillic as their native font, right? So it's not quite clear, technologically speaking, how we deal with some of those issues. So yeah, there's a bunch of other sort of security issues that are very subtle here. One thing that's interesting is, if you look at plugins. So how do plugins treat the same origin policy? Well, plugins often have very subtle sort of incompatibilities with the rest of the browser with respect to the same origin. So for example, if you look at a Java plugin, so Java oftentimes assumes that different host names that have the same IP address actually have the same origin, right? That's actually a pretty big deviation from the standard interpretation of the same origin policy, right? Because this means that if you have something like x.y.com and let's say z.y.com, if they map onto the same IP address, then Java will consider these to be in the same origin, right? Which is a problem if, for example, this site gets owned, but this one doesn't, right? So there's a bunch of other sort of corner cases involving plugins. You can refer to the Tangled Web to see some more about some of those types of things. So the final thing that I want to discuss, you can see the lecture notes are more examples of sort of crazy attacks that people can launch. But the final thing that I want to discuss is the screen sharing attack, right? So HTML5 actually defines this new API by which a web page can allow all the bits in its screen to be shared with another browser or shared with the server, right? This seems like a really cool idea because now I can do collaborative foo. We can sort of collaborate on a document at the same time. That's exciting because we live in the future. But what's funny about this is that when they designed this API, and it's a very new API, they apparently didn't think about same origin policies at all. And so what that means is that if you have some page that has multiple frames, then any one of these frames, if they are granted permission to take a screenshot of your monitor, it can take an entire screenshot of the entire thing, regardless of what origin that other content's coming from, right? So this is actually a pretty devastating flaw in the same origin policy, right? So there's some pretty obvious fixes you could think about. So for example, if this person's given screenshot capabilities, only let it take a screenshot of this, right? Not this whole thing. Why didn't the browser vendors implement it like this? Because there's such pressure to compete on features and to innovate on features and to get that next new thing out there. So for example, a lot of the questions that people were asking about this particular lecture online in Piazza was like, well, why couldn't you do this? Wouldn't this thing make more sense? It seems like this current scheme is brain dead. Wouldn't this other one be better? And the answer is yes, everything, yes, it's exactly correct, right? Almost anything would be better than this. I'm ashamed to be associated with this, right? But this is what we have. And so what ends up happening is that if you look at sort of the nuts and bolts of how web browsers get developed, people are a little bit better about security now. But like with the screen sharing thing, people were so pumped to get this thing out there, they didn't realize that it's going to leak all of the bits on your screen, right? And so now we're sort of at this point with the web where, I mean, look at all these things that we've discussed today, right? So if we were going to start from scratch and come up with a better security policy, what fraction of websites that you have today are going to actually work? Like approximately 0.2% of them, right? So users are going to complain. And this is another constant story with security, right? Once you give users a feature, it's often very difficult to claw that back, even if that feature is insecure, right? And so today we discussed a lot of different things about the same origin policy, stuff like that. Next lecture we'll go into some more depth about some of those things when we talk about Django.